Recording. Good morning, Organic Chemistry 2341. This is our last lecture. This is our last lecture of the semester. On Thursday, we're going to have our exam number 3 over predominantly chapters 8 through 11. And then the next time we meet will be for the final. Okay, so obviously the exams will be on Top Hat unless otherwise arranged. And so we'll just on Thursday, log into Top Hat and take the exam you're assigned with. On our exam day, which I want to say is the 6th for this class, at 8 a.m. in the morning. But let me double check that. I don't want to give anybody bad information. I'm going to pull up our Canvas page and on lecture and exam schedule. So yeah, on the 29th of April, we're going to have our 3rd exam over chapters 8, 9, 10, and 11. And our final exam is on the 6th, May 6th, comprehensive from 8 a.m. to 10:30 a.m. So write that down. Okay. Again, it'll be a Top Hat exam. It'll be 60 questions. You'll have 2.5 hours to complete that unless you have accommodations, and then you'll have your accommodation. It is going to be multiple choice, unfortunately, no drawing or anything like that. So I'm kind of really looking forward to getting back to in-person teaching so we can have quizzes with drawing and you can have more practice doing that. But so that's what we're going to have to do for now. And so are there any questions about the exam? Again, the exam and the final are in the same, kind of tone as our homework and our last 2 exams. So, there should be no surprises there. I will live monitor. So if you get kicked out, I can go ahead and get you kicked back in.
Sorry, I came in a minute late. Did you say that the exam 3 is going to be over 8 through 10, not 11?
8 through 11.
Okay.
8 through 11. Yeah, it's going to be these last chapters. So we're going to get all the way through 11 today. So we have 11.1, which is the finishing up of these alcohols, and we're going to talk about ethers and how to make ethers. But again, the most important ether reaction is the one we just started and the one we're going to continue on today. Okay, so go ahead. If you have any more questions, just put them in the chat or chime in. That's fine. We only about 27 of 99 of us here, so we have plenty of opportunity to talk. So let's go back to reactions to form alcohols. And one of the reactions, okay, so we used granular reagents or organometallic reagents to add across a carbonyl, and that was one way to make alcohols. And we can make primary, secondary, and tertiary alcohols. And then we add reducing agents, hydride transfer agents, that negative hydrogen, to add across our carbonyl to also produce primary and secondary alcohols. Okay. And then we can also find out that one of those reducing agents, the lithium aluminum hydride, can also reduce down esters and carboxylic acids to primary alcohols, but the sodium borohydride can't. So we have selectivity in our reagent. Okay, so that was one of the most important part of that reduction. And then we started talking about ring opening of the oxirane or the epoxy. Okay, so it's a nucleophilic attack. We found out if you attack it with a nucleophile, it's going to open up. The nucleophile is going to be on 1 carbon over from where the alcohol is, and it will create a wide variety of functional groups for us. Alcohols with something else, like an alcohol or an ether or a nitrile. Now, turns out there is selectivity in that reaction. Under basic conditions where the oxygen of the oxirane is not protonated, it's all about sterics, meaning the nucleophile is the only thing that matters. Nucleophilicity is a kinetic thing, so it's going to go to the least substituted side, giving you a more substituted alcohol. Under acidic conditions, however, the oxygen in the oxirane gets protonated. And when that oxygen of the oxirane gets protonated, it's going to elongate that bond and create a partially positive charge on one of the 2 carbons. It's going to create the partially positive charge on the more stable carbocation center, which is going to be the more substituted carbon. So you can selectively make the more substituted alcohol under basic nucleophilic conditions, or the less substituted alcohol under acidic, weak nucleophile conditions. Notice I said weak nucleophiles here because what we want to do is we want to have that polarization, and then we want to have the weak nucleophile come in and wait for that partially positive charge to generate our center. Okay, so when we do this with something simple like just an acid-catalyzed system in water, the first thing we get is that protonization of the oxirane, and then we have attack by water, the weak nucleophile, to generate a protonated dialcohol, okay? So notice we're attacking it with water. Water is one of those weak nucleophiles, okay? So then the thing that can happen is water can act as a base right here and deprotonate our alcohol, giving us our diol, okay? Notice when we do that, we regenerate an acid. So you only need a drop of acid in this to do this kind of system, okay? It also works with alcohols because the alcohol can act as a weak nucleophile, and it'll create our protonated ether species, and then our alcohol will act as our base. We will regenerate our acid, and we end up with an alcohol and an ether. Okay, so the two carbons of the oxirane are going to be between the oxygen and the alcohol and the oxygen of the ether. Okay, so that way we can actually extend this and go really, really far. However, if you do it in the presence of a protic acid like HBr, HCl, and HI, what you're going to end up with is a halohydrin reaction, where we're going to get a halogen on the number 2 carbon and the oxygen on the number 1 carbon. And it's the same mechanism. We get that protonation first, and then our weak nucleophile of our iodine, bromine, or chlorine is going to come in and interact with the system to give us our final product. Okay, so mechanism's pretty easy, and we've seen why the selectivity happens under those two different conditions. Okay, there we go. Okay, now we can think of this unsymmetrical acid-catalyzed ring opening to be similar to what we saw in the oxymercurization, demercurization system, or in that bromonium ion. Because we have some kind of center on top that is protonated, it's going to elongate one of those bonds, and it's going to elongate the bond that gives the better, more stable carbocation. It's not a full carbocation, it's only a partially positive charge, but it's the same type of system we saw in those two other systems, where we'll get the second thing coming in on the more substituted carbon. Okay, now that means there's probably some stereoselectivity as well. Okay, because the nucleophile has to come in from the bottom because the 3-membered ring is still on the top. So we have to have the nucleophilic attack come from the bottom. We have anti-addition. Okay, so let's look at that. Under the acid-catalyzed conditions, the first thing we're going to do is we're going to start with this stereocenter here. Okay, so we have ethyl and methyl, and then we're going to have the oxirane. And that's going to give us a R configuration for our particular system. Don't forget to study your stereochemistry for the final exam. Okay, so the first thing that's going to happen is we're going to protonate that alcohol, and then we're going to elongate that bond. We're going to have a partially positive charge on each of them, but this would be generating a tertiary carbocation. So more of the positive charge is going to be on the tertiary center. Okay, there it's still bonded to it, and so the oxygen, the protonated oxygen, is still blocking the top of the system, which means our nucleophile has to come in and react on the bottom. Okay, when it does that, it's inverting that stereocenter because it's an SN2 reaction, and all SN2 reactions invert the stereocenter. But we also have that anti-addition to where our alcohol is going to end up. Okay, so questions on why it's regioselective and why it's got a stereospecific attack. Okay, so what we see here is under basic conditions, it's all about sterics. Your nucleophile wants to attack the least hindered site. Under acidic conditions, we now have the formation of a partially positive charge, and we want to form the more stable partially positive charge because of hyperconjugation. So that means that each of those reactions, in the basic, it's regioselective because it goes to the less substituted carbon, generating the more substituted alcohol. In the protonated system, it's also regioselective because it wants to make the more stable partial charge, and therefore the nucleophile attacks the more substituted side. And in both cases, because we have a ring on top, it's going to be stereoselective because it has to come in with our SN2 and invert the stereocenter. And it's either on the least substituted carbon for the basic conditions or the more substituted carbon for the acidic conditions. Okay, now this is really easier to see sometimes on our rings because we don't have free rotation, and so we have that fixed in space, so we don't have to worry about redrawing several options here. So in the case of this first enantiomer here, when we look at it, we have the methyl group here and the hydrogen here, so that makes the two centers different, and that gives us S for the one on the left and R for the one on the right. Okay, now because the one on the right has the more substituted carbon, our nucleophile is going to attack that more substituted carbon under these protonated conditions, meaning we're going to have anti-addition and we're going to invert our stereocenter. Okay, so we've inverted, see how the methyl group has flipped up because we attacked from the back here, therefore inverting that stereocenter. Notice the stereocenter does not change here, okay? So the one on the left still stays S, but the one on the right has inverted its stereochemistry, giving us S as well, okay? Now, if we had the other enantiomer of the material, where we had the R on the right, the left, and S on the left, we're going to see that same attack at that same carbon, and we're going to also see inversion at that same carbon. So because it's more substituted, our bromine is actually not going to attack from this side. It's going to attack from this side because the oxidation is blocking, therefore flipping the methyl group down, giving us anti-addition. So our bromine added anti to our leaving group here, and it gives us that inversion of stereocenter. So this is still R on the left, and now our right has turned into an R as well. Okay. Okay. So does that show you the regio and the stereospecific attack of the system? Oh, it lets me in, sorry. There we go. All right. All right, so that's kind of one of the really cool things about this ring opening of the epoxy to make alcohols and actually make functionalized alcohols. See, we have a halohydrin in this one, so you can actually do substitution chemistry on that bromine if you want, or elimination chemistry to make other products. Okay, so this slide is actually out of order. It should have been with the other oxidizers. The one we talked about in the oxidation system was this Jones reagent here. And we talked about how that chromic acid would oxidize it down immediately to an aldehyde, but then because of water, it would oxidize it again to the carboxylic acid. That's not the only oxidizer we have in our thing. We also have potassium perchromate right here. So imagine it's kind of like almost double what that is with two potassiums counterbalancing the charge, but it's also under acidic conditions. So it's going to do the exact same thing as the chromic acid. The other way we can do it is we can actually do it with a basic conditions. And when we do that, we're going to use that potassium permanganate. Remember, we used potassium permanganate in the alkenes chapter, and we saw that it makes in the case of an alkene, it breaks the double bond by oxidizing it down to carbonyl compounds. In the case of our alkynes, it actually made a tetraol, which then converted into a dione. In the case of alcohols, it converts them to carboxylic acids or ketones because it also has water in it. So we will always convert our primary alcohols down to carboxylic acids, our secondary alcohols down to ketones. But remember, our tertiary alcohols don't react with any of these reagents. Okay, questions on that? I'm sorry, I just noticed that was out of order on the last lecture. But okay, so now we've made alcohols into different functional groups. We've taken carbonyl compounds, made them into alcohols, two different ways, by substitution and by reduction. We've taken oxygen alcohols and turned them into ketone or carbonyl compounds, and we've ring opened to give highly functional groups with our oxiranes. Okay. Now, let's say we wanted to do some kind of reaction. We had an alcohol and we wanted to remove it somehow, but we know that hydroxide is a bad leaving group. It's not going to be like, we can't do SN2 reactions on just an alcohol because that's a bad leaving group. It's a really strong base. It won't go. So how can we trick our alcohol into being a different functional group that still has the oxygen on it, but is a better leaving group? Okay. And so what we do with that is we actually convert them into something that would not mind leaving, something that is a weaker base than hydroxide, and then we can have it act as a leaving group. Okay, in that case, there's a couple different ways we can do that. We know that we can take a primary alcohol and convert it to a halogen using this acid-catalyzed substitution reaction, okay? Because we protonated the alcohol, it made it into a neutral leaving group, water. So under acidic conditions, we can do that, okay? However, it only works with either HBr or sodium bromide because it's the only one that's reactive enough to do it. It's the only one that's a strong enough acid and a strong enough nucleophile to make that work. In the case of trying to put a chloride there, we actually have to use a Lewis acid catalyst for it. In this case, it's zinc chloride. And we're using zinc chloride because we want to encourage a zinc oxygen bond, which makes it a better leaving group. So the way that works is we add zinc chloride and HCl to our system. And when we do that, the zinc chloride acts as the Lewis acid, the alcohol acts as the Lewis base, and we form a acid-base complex. Once we do that, now we have a way to have neutral oxygen species leave the system. And when we have an ability for a neutral oxygen system, a non-hydroxide oxygen to leave, then we can have our nucleophile of our chlorine come in and displace it in an SN2 reaction. Now, once it does that, there we go, it creates this zinc hydroxide dichloride, which is a negative charge, and it gets protonated and it turns back into zinc chloride and water. Okay, so we have a regeneration of our Lewis acid catalyst. Okay. So again, chloride is not a strong enough nucleophile to just have that protonated water come off, so we have to increase it. Remember, bromine and iodine are good nucleophiles. Chlorine and fluorine are moderate nucleophiles. Okay. So are there other ways to do this? Well, yeah, there is. We can try to create some other way of making that oxygen a really good leaving group. And one of them is to use a phosphorus halide. Okay, so you can easily buy phosphorus pentachloride or phosphorus trichloride, which are these two here, or you can make it in situ by adding phosphorus and iodine. The actual phosphorus iodine is not very, triiodide is not very stable. It's a reversible reaction, so you don't just have it in a bottle, which is why we do it in situ or make it when we're running the reaction. So in the case of this, we can take 3 equivalents, that's not a tertiary, 3 equivalents of an alcohol, and it'll do a primary or a secondary alcohol and convert it to a halogen, 3 equivalents of that halogen, and this phosphorus trihydroxide, which is once it hits water, it turns into phosphoric acid. Okay, we can do it again with bromine if we want a bromide on there. And again, it's a 3 alcohols will convert to 3 halides and an equivalent of the phosphorus. In the case of pentachloride, it actually only goes once because it creates another species called phosphorus oxide trichloride, which is then actually not reactive enough to displace another one. Okay, so the oxygen actually kicks out HCl and we get a double bond between the oxygen and the phosphorus. Okay, now in the case of the phosphorus and iodine, it's in a reversible reaction, but once you have a little bit of this in there, it'll convert your primary or secondary alcohols to an iodine. Okay, so in all these cases, we are tricking the oxygen to leave by making it either a better leaving group, water in the protonation part, or having an oxygen bond to some other element, for example, the zinc, or in this case, the phosphorus. Okay. So the idea is to make it not leave as hydroxide, make it leave as something else. Okay. So in the case of the phosphorus tribromide, it can react all 3 times. It's going to create a phosphorus dibromo hydroxide and then a phosphorus bromo dihydroxide, and then it'll go to the phosphorus trihydroxide. Now the phosphorus trihydroxide actually then rearranges and forms a major isomer of the minor isomer of the phosphorus trihydroxide, or it rearranges and turns into something more like phosphoric acid. Either one is the same, it's just got a tautomer in there. Notice the difference is that phosphorus has 5 bonds in the more stable version and only 3 bonds in the less stable version. Remember, phosphorus is 1 row down and it has available d orbitals to give it higher than an octet. And that's why it's actually more stable in that form. Okay. Now, the reason I said it only works for primaries and secondaries is the fact that it is an SN2 reaction, because we create the phosphorus oxygen bond first, right here. When we create that phosphorus oxygen bond, that makes it into a neutral leaving group. So we'll have the bromine act as our nucleophile in an SN2 reaction to kick out that phosphorus dibromohydroxide as a neutral species, okay? So when we do that, that creates something that is still reactive. These these bromines are still reactive and can react 2 more times. And again, primary and secondary only because it's an SN2 reaction. All right, questions on the creating halogens from the alcohols? Okay. So what's interesting is this phosphorus tribromide reaction is stereospecific because it's an SN2 reaction. So we always get a inversion of the stereocenter. Because it's an SN2 reaction, we're not forming a carbocation, so we don't rearrange. And because there's no strong base anywhere nearby, it doesn't undergo any E2 eliminations. So it's a fairly clean reaction of substituting that alcohol and taking it all the way to the halogen, and in this case, the bromide. Okay. Now, I said that that worked pretty well with the phosphorus there, but with the chlorine, we had to use a catalyst to make it work. Well, there's another way to make the alkyl chlorine by making it into a better leaving group. And the reagent we use here is called thionyl chloride, SOCl2. Okay. So for every equivalent of alcohol, you use 1 equivalent of SOCl2, and you will generate your alkyl halide, alkyl chloride, SO2, which is a gas and comes off, and then HCl. And then HCl, there it is. All right. So, but just like in the phosphorus reaction, it is also a substitution reaction, an SN2 reaction, and therefore we get inversion of stereocenter. Okay. Typically, if we do it under basic conditions, it will give us an SN2 reaction. If we do it under neutral conditions or acidic conditions, it actually doesn't do an SN2 reaction. we retain our stereo center through a very unusual part of the mechanism. So in the case of using, if we see SOCl2, it's an SN2 reaction, and therefore we get inversion of configuration. We still generate SO2 gas, and then we have the salt of HCl with the pyridine. That's one of the purposes of the pyridine. In the case of not having that base there, we now have gaseous HCl. So what's the mechanism? Okay, so in the case of the basic conditions, what we have is the first thing we do is we react the SOCl3 as a Lewis acid with our alcohol, the Lewis base, and we create this acid-base complex here. So now we have that positively charged oxygen there. Okay, in this case, if we have a base, we can deprotonate that oxygen, generating our neutral intermediate, which is our alkyl chlorosulfate. Okay, now our alkyl chlorosulfate then can interact with pyridine, and we can kick out our chloride ion, which can then generate HCl and our neutral species. This is our pyridinium alkyl sulfate. Now notice, the only part of this that is charged is way over here. The chlorine is counterbalancing the charge here. And one of the hydrogens is on one equivalent of pyridine. This is the other pyridine. So now what we have here is we now have a really good leaving group. It's going to leave as, if we have a SN2 substitution here, this is going to kick over here, generating SO2 and generating our neutral pyridine again. Okay, so let's look at that SN2 reaction. Our nucleophile, again, chlorine, not a very good nucleophile, so we had to have a really good leaving group. It leaves as this species, which immediately rearranges to clip this bond and give us SO2 and our neutral pyridine back. So pyridine is actually a catalyst in the system, but the whole point is we're generating this alkyl sulfate as our intermediate, and we have SN2 reaction that kicks out SO2 and pyridine. So if we don't have the pyridine, that means we don't do this step here. So that means we're going to change the chemistry. Okay. So in the case of thionyl chloride in an aprotic solvent, like ether right here, what we'll see is that first step happens again. The thionyl chloride is going to act as our Lewis acid. Our alcohol is going to act as our Lewis base to generate this compound, but we are not going to deprotonate this with pyridine. So we have to figure out some other base to deprotonate it with. So what we're going to end up doing is using the negative charge on oxygen is going to come in and create a double bond and kick out chloride ion. The chloride ion becomes our base. Okay. So now that our chloride ion is generating our base, we generate our alkyl chlorosulfate here and HCl gas. Okay. That is a different compound than what we formed with the pyridine. Remember, the pyridine actually came in and acted as a base and created a bond with sulfur. We can't do that now. So what we see here is it actually eliminates giving us a loss of the chlorosulfate, and we generate a carbocation. Okay. Now in this case, it's a secondary carbocation. It's not the best carbocation, but this was such a good leaving group and decomposes immediately into SO2 and chloride ion. Now notice, we don't get a rearrangement here because we're generating the chloride right next to where our carbocation formed, okay? So it had just split off, that carbocation is really reactive, and we have what we call a intimate close contact ion pair, or an intimate ion pair, which means they haven't had time to diffuse away. When they do that, the chlorine acts as our nucleophile and attacks on that same side where it was originally, because it hasn't moved away from that position. And we end up with the retaining of the stereo center. So it's technically an SN1 reaction because we form a carbocation, but we don't have time for it to rearrange. And once the chlorine attacks back onto the center here, we can break this bond and generate SO2 again. We generated HCl before, we generated SO2 here, and we get retention of stereocenter. Okay, so we started with the S, we ended with the S. Now, the whole trick is it still goes through the carbocation, but they don't diffuse away from each other. It immediately reacts from the side it split off on. Okay, so that's why we have retention of stereocenter. All right, questions on either of those mechanisms? Whoa. All right. Okay, so when you see thionyl chloride, look to see whether it has pyridine or not. If it has pyridine, you're going to put a chlorine there and you're going to get inversion. If it doesn't have pyridine there, you're going to put the chlorine there and you're going to get retention. Okay. So another way to do it is to create a better leaving group by forming, instead of one of those alkyl thiosulfates, we're actually going to do what we call sulfonates. So we're going to do derivatives of sulfuric acid. So sulfonates are derivatives of sulfuric acid that have at least one sulfur carbon bond. Okay, and so that can be a methyl group, that can be a phenyl group, that can be anything, a bunch of different things, and I'll talk about those in a minute. So, but the joy of using the alkyl sulfonate is you start with a chlorosulfate and it only reacts once to create a stable bond. Okay, so in this case here, we can create a sulfate, alkyl sulfonate, sorry, by a one reaction with the oxygen here to liberate HCl. Notice we do pyridine as our base here, and it creates this stable compound here. So what has this done for us? If we were to attack this alcohol in an SN2 reaction, we'd be kicking out hydroxide as our very strong base. Okay, but if we kick this out, we had a sulfuric acid derivative. Sulfuric acids are very strong acids, which means they're very weak bases. We've taken that oxygen and converted it from a strong base to a weak base. And because it's a weak base, it's a better leaving group. Okay, so all of these are, that's what we're doing. We're creating a weak base as our leaving group. Okay, so let's see how to use that to our advantage here. Come on. There we go. Okay, so what we'll see here is in all cases, we can use some carbon bond with sulfur here. In this case, we can, if we use a methyl group, that's called methane sulfonic acid or the mesylate. That's one of the things we'll actually use that a lot in the second half. Then there's para-toluene sulfonic acid, which would be the tosylate. Oh, I'm sorry, these are the chlorides. So we can actually have that functional group there. And if we have a trifluoromethyl group here, that's called a triflate or the trifluoromethane sulfonyl chloride. Okay, so notice all we're doing is changing these, and we change them because they make them slightly better or worse leaving groups, and they are soluble in different things. But these are the three most common that are used in that system. Okay, now in all of them, what you do is you end up generating a stable sulfonate in that system, and then you can go ahead and add your nucleophile. Okay. So we get retention of configuration because what we end up doing is our alcohol acts as our Lewis base and attacks the sulfur, which is our Lewis acid. We get a protonated alcohol, and then the best thing we can do is actually kick out a chloride ion to generate chloride ion as a base. I guess we're not generating chloride ion, but it kicks out chloride ion to regain our two double bonds to oxygen with sulfur. Okay, we have pyridine in the system as our base, which deprotonates the alcohol, and we end up getting the sulfonate in the exact same configuration the alcohol was. So we're not displacing the alcohol yet to create that sulfonate. And so the way we can think about that is just a derivative of sulfuric acid. Okay. So now once you form this here, now you do any kind of SN2 reaction with any good nucleophile, you get inversion of stereocenter when you do the attack by your thing. All you've done is made your alcohol a better leaving group because you've made the OH, a strong base, into a sulfonate, which is a weak base. Questions on the sulfur derivatives? You know, it's kind of this along the same lines as the thionyl chloride, except with the thionyl chloride, we're actually incorporating our nucleophile into the system. In this, we're not. We're creating an actual just good leaving group, and then we can hit it with any nucleophile we want. Okay. All right. So if we can remember, another reaction we can do with alcohols is we can do a dehydration. We already talked about this. And so when we do that, we want to dehydrate our alcohol. In the case of acid, we can have carbocation rearrangement, but we tend to form our Zaitsev product. Our Zaitsev product is our more stable product, our more thermodynamically stable product. So it's usually the more substituted, or in the case of disubstituted, it's our trans isomer. Okay, so that is all the reactions we have of alcohols. Questions on reactions of alcohols? Okay, let's move on to our last module, module 11.2, ethers. Okay, so we already talked about the Oxiranes, so I'm going to kind of not talk about that very much, but ethers actually have a bunch of other properties that are useful to us. The first and most important is they react with very few things, making them great solvents. Remember, in the case of Grignards, we had to have a solvent that was polar but did not have acidic protons. Ethers are polar but don't have acidic compounds. They are very stable under basic conditions because the leaving group would be an alkoxide. Okay, so if we were to attack this with a nucleophile to try to kick an alkoxide out, that's a strong base. Poor leaving group makes it less reactive to nucleophilic attack. Okay, still can, but it's just less reactive. Under mild acidic conditions, we can actually have no reaction as well. But under strong acidic conditions, you're going to protonate that alcohol, or you're going to protonate that oxygen. And by protonating that oxygen, you're making it a better leaving group. That's why under strong acids, when you're protonating that alcohol, you're protonating the ether, it can break that ether bond. Okay. So the two most common you'll see are diethyl ether here, and this one right here is THF, tetrahydrofuran. It's used as a very common solvent, usually called THF. Whenever you see that, think polar non-protic solvent. You can do Grignard reactions in it, lots of nucleophilic attacks in it, and you can use that as your to control an SN1 versus SN2 reaction because it's not protic. Okay, so one of the things you can do is under strong acidic conditions, you have to use a strong acid, HI, HBr, or H2SO4. HCl sort of almost works, but it's very poor. It's not acidic enough, and so it will react slowly over time, but it's not very useful. Okay, so what we do is we, of course, can take excess HBr, and we'll end up with an alkyl halide, because the HBr is going to displace the alcohol generated when we do it. Okay, so let's figure out stepwise. The first thing we're going to do is protonate that alcohol to make it a leaving group, right? So once we protonate this alcohol, we have that oxonium cation here. Now we can have our bromine act as a nucleophile, and we're going to end up with an alcohol and an alkyl halide. But as we saw in the previous module, HBr reacts with the the alcohol to protonate it too, and then displace the water with alkyl halide. That's why the net reaction is two equivalents of the halogen, of the halide, from one equivalent of the ether. Okay, and HI is the fastest, HBr is pretty good, and HCl is much, much less. We have to probably, it doesn't work very well at all. Now, in the case of the, okay, so how do we make ethers? Well, when we make ethers, we want to actually basically do a nucleophilic attack on something with a leaving group. And as we saw before, most of the time, like halogens are good leaving groups, right? And so we attack them with an alkoxide. We deprotonate an alcohol. That's a good leaving group. I mean, sorry, that's a good nucleophile. Strong base, but good nucleophile. So it works best on primary alcohols, or primary alkyl halides, so they're less likely to form elimination products. Or we can use our new sulfonate esters, which are also now very good leaving groups. Okay, so we take a deprotonated alcohol, a primary group with a good leaving group, and we get an SN2 reaction. Okay. So let's draw one up here. We can use alkoxide as our SN2 reaction. We generate our ether. Okay, so that's if we have two molecules. Okay, what if we have an alcohol on a on the same molecule with an alkyl halide? Well, we can actually get an intramolecular reaction to form a cyclic ether. Okay, now this intramolecular reaction is 5,000 times faster than the intermolecular interaction. Okay, and here's why. In the intermolecular interaction, you have your alkyl halide here. It has to diffuse to where your nucleophile is. They both have to have enough energy to enter that transition state to start forming a bond and start breaking a bond, and then they have to cascade down to products. Okay. In the intermolecular, you have your nucleophile in close proximity to your leaving group, and so they're just flopping around all the time, and so the number of times that they are actually going to have contact is higher, and so they, they'll be able to have a greater number of chances to form that bond, even at that same temperature, because you have a greater number of contact areas because they can't diffuse away from each other. They're right next to each other all the time. Okay, so does that make sense? We make ethers using substitution reactions, and they're SN2 reactions. Okay. So the actual, way we would do this would we take some kind of, the best way to do it is to either take sodium or potassium metal or sodium hydride to the alcohol. The reason is those are irreversible bases, okay? Meaning if we take sodium hydride, that's going to react with the alcohol and generate hydrogen gas and that salt, okay? If we were to use something like a protic water solution, or just potassium hydroxide or something like that, that could act as the nucleophile too, and you wouldn't get the substitution product you want. So we want to use an irreversible base. In the case of sodium, it's going to do a proton transfer, and we're going to end up generating hydrogen gas as well, and that's sodium salt or potassium. We want to do this in an aprotic solvent, and so we use one that can support ions, but is still aprotic. So think of, this, in this case, it's DMSO, dimethyl sulfoxide, or you could use other ethers that you already have, but then you have to separate them. So once you make that, notice it's irreversible, and so you have all of your material as your nucleophile. Then you slowly drip in your alkyl halide, and you make your ether in high yield. Okay, so it's the same. It doesn't work the same in the cyclic ether because it's such a much faster reaction, and because the proximity of the alkoxide formed, you can use the reversible base of having OH, but it's going to act as the base first, and then the alkoxide will act as the nucleophile, and you'll get the cyclization happening. So linear ones, you want to use your irreversible bases that make just the alkoxide by itself, and then add your halide. In the case of the cyclic systems, you can use base because of the close proximity of the two reactive groups. Okay, and it's also favored by entropy. Okay, all right. So the problem is there can be competing reactions if you have the spacing between the alkyl halide and the alcohol gives you like if you're trying to make a 7-membered ring, you're more likely to actually make a long chain as opposed to that 7-membered ring, because 7-membered rings are hard to make. So if you're trying to make a 5-membered ring or a 6-membered ring, the intermolecular reaction is going to be faster. If you're trying to make a ring that's bigger than that, extending the chains, not making the ring, is actually going to be the faster reaction because of entropy. Okay. So in the case of if N is, let's see, 6 would be, N would be 4, you actually have the competition between the intermolecular reaction and the intramolecular reaction, and the intramolecular reaction is favored because it's faster. Okay. If N is greater than 4, you actually are going to get longer and longer chains to create that system. The other reaction that could happen, which I said before with when you have that hydroxide there, the hydroxide can act as a nucleophile. And if the hydroxide acts as a nucleophile, it can displace the halogen, giving you an alcohol on both ends. And that terminates the reaction or can create side reactions because either of those alcohols can now react with an alkyl halide. Okay, so designing your system to try to give you the cyclic first or give you the longer chains is about designing how many spaces you have between your alkyl halide and your alcohol. Okay, now you can make epoxies using this system. Okay, if you start with a halohydrin, which is a hydroxy on one and a halogen on the other, you can deprotonate that and be able to get into it to form that high ring strained ring. Okay, it seems unfavorable, but the idea is that it's in such close proximity and it's already an anti-configuration that you can form the ring fairly well, and those rings are stable under these conditions. So that's one way to make epoxies. Remember, we also made epoxies using per acids when we added an oxygen across the double bond in chapter 9. Okay, so let's remind ourselves of that reaction. When we have an alkene, we typically use something like metachloroperbenzoic acid, or MCPBA. Okay, and what we're doing is we have an extra oxygen here. This is the partially negative oxygen. This is the partially positive oxygen. The partially positive oxygen attacks the partially negative double bond, transfers it in a single addition, giving us our epoxy. Okay, and our carboxylic acid out. So that's another way to make that epoxy. So we can do it with a ring with the ether synthesis, or we can do it with that oxidation reaction. Okay, so okay, great. We know how to make these, and we have, what other use could we use for ethers? And so sometimes you want to do a reaction, like let's say we have a carbonyl on one side and an alcohol on one side, and we want to do a Grignard on the carbonyl. But because there's a proton on that alcohol, we can't do that reaction because it'll just react with the alcohol and be done. Okay, so what we can do is we can actually make an ether, which no longer has that proton on it, on the alcohol side, and then we can do other reactions on the other side. This is a strategy called use of protecting groups. we're going to make our alcohol non-reactive. We're going to react some other part of the molecule in the way we want it to react, and then we can regenerate that alcohol. Okay, so this is called protecting group. Okay. So one of the best ways to do that is with ethers, because ethers have very low reactivity under mild acidic conditions and basic conditions. So that's why ethers are typically used in this protecting group system. Okay. So one of the good ones to use is you take isobutylene, which is just this double bond here, and through a carbocation mechanism, you generate an acid-catalyzed carbocation. This carbocation then acts as our Lewis base to react with our oxygen to give our protonated ether. And then when we regenerate our acid catalyst, we end up with our ether here. Now, there is a possible side reaction in the fact that it can react with the alkene of another isobutylene, and that'll actually end up continuing to react and make a little bit of a mess. But that's fairly slow in comparison, and we make this in high yield. Okay. So notice we're making this T-butyl ether when we make the isobutylene, because we have 1, 2, 3 carbons here, and that gives us, and our carbocation was on the center carbon, and so we make this T-butyl ether. Okay, this T-butyl ether is very poor reactivity until we want to take it off. We take it off under special conditions. Okay, so remember that ethers are not stable under strong acidic conditions. So all we need to do is add a strong acid and water, and what we'll do is we'll regenerate the alcohol that we just protected, and we'll also generate the T-butyl alcohol. We don't regenerate isobutylene, we generate a T-butyl alcohol. The way that works, of course, is we protonate our oxygen, making it a better leaving group. Now our bond can break here, generating our carbocation again and our alcohol. And then our carbocation reacts with the water in the solution to generate our T-butyl alcohol. Okay, but remember, this is a strong acidic condition. We used a strong acid in the absence of water to generate the ether. We use a strong acids in the presence of water to break it off. Okay, so how would we use this? Well, let's say we have this bromopropanol right here, and we wanted to make an ether out of it. Okay, so, oh, well, let's just add base to it. Well, we can't do that because we can form a 4-membered ring. That's an intramolecular interaction. That cyclization is going to happen very, very quickly. That's probably going to be our major product. Even though it's a strained ring, it's an intramolecular interaction, and it can react. Well, the other thing that can happen is it can react with another molecule of itself and generate a extended ether that is also not the ether we wanted. Or it can actually react with ethanol and get the ether we want, but it then can go on to react with other things as well. Okay, so we have 2 possible side products and the product we want. Okay, so how can we force it just to give us the product we want? We protect the alcohol. So what we do is instead, our first step of our reaction is we take isobutylene and concentrated sulfuric acid. Now, concentrated sulfuric acid only has like 1 or 2% water in it, and it's a strong dehydrator, so it counts as being a non-aqueous solvent. We generate our T-butyl ether. That means this is completely non-reactive when we put the base in it. Now we're going to put our alkoxide in the solution. Our alkoxide acts as our nucleophile, does our SN2 reaction to generate an ether. So now we have 2 ethers. Those 2 ethers are now non-reactive to anything else in the solution. We take that product, we heat it up in aqueous H2SO4, aqueous sulfuric acid. It clips off the T-butyl ether preferentially. Why does it break off the T-butyl ether preferentially? Because the T-butyl ether will form the tertiary carbocation, which is that intermediate. The other side would generate a primary carbocation. So the T-butyl ether clips off preferentially because of that carbocation intermediate, and therefore we get our desired product. Okay, so this strategy is going to be used a lot next semester, so you need to put some of this into memory. Okay, another way is instead of making a carbon-based ether, we can make a silicon-based ether. And they have a different removal method that makes them a little bit easier to use sometimes. So in the case of this, we usually have a chloride on the silicon center. And in this case, we're using trimethyl chlorosilane. So we have one chlorine on there, we have 3 methyl groups on there, and that acts as our Lewis acid. Our alcohol attacks in an SN2 fashion, kicking out chloride, and then adding a little base removes this proton and gives us our neutral species and a salt. Okay. So these are quite stable to most conditions, basic conditions, and mild acidic conditions. Okay. But the joy about this system is that silicon has a very strong bond with fluorine. Okay, and so what we can use is we can actually use a fluorinating agent or something with fluoride ion in it to break that bond. Okay, so in the case of this, we're using what we call tetra-butyl ammonium chloride, and that looks like this right here. This is tetrabutyl ammonium fluoride. It's basically 4 butyl groups around nitrogen generating a positive charge, and then the fluorine is the counterbalancing ion. Okay, so the driving force for this is forming that much, much stronger silicon fluorine bond, kicking out your alkoxide as a salt, and then when we protonate at the end, we generate our alcohol. Okay. Now, just like other ethers, the silyl ethers are also fairly strong to mild acidic conditions, but if you have a strong acidic condition in the presence of water, you will get that same attack and you will generate a silicon oxygen bond and you will regenerate your alcohol. Again, the driving force is the water has to be in higher concentration than the alcohol, and it'll drive the reaction to completion. Scratchy throat today. All right, questions on that? Okay, so you can use either the T-butyl ether or the silyl ether to do these protections of alcohol groups and then do nucleophilic substitution on the other side of the molecule, or do specific reactions that'll attack carbonyls, like a hydride reduction or something like that on the other side of the molecule, and then come back and clip it off. Again, fluorine clips off the silicon-based ethers, but not the other ethers. Okay, so let's put this to practice. Okay, we have a carbonyl on one side, so we have a ketone on one side, we have an alcohol on the other, and we want to convert that ketone into a tertiary alcohol. So, okay, we know how to do that. We're going to hit it with a Grignard reagent and make it into the tertiary alcohol. But wait, if we just added the Grignard reagent to the alcohol, it would then transfer the proton, create methane and the salt of the alcohol. So it's not going to work. So we use in this case, we're using the silyl ether, trimethyl silyl chloride, chlorosilane, and we're going to create that ether with the silicon bond on it. And when we have that group, we call it the TMS, trimethyl silyl ether now. And then that is now not reactive to SN2 reactions. And therefore we can actually go ahead and do our addition reaction on our carbonyl. And after acid workup, we can generate both alcohols. So we now have our tertiary alcohol from our carbonyl compound and our primary alcohol that we had to protect to be able to get to that tertiary alcohol. Okay, questions on protecting groups? Okay,
So you said for that last part with that primary alcohol at the end, it's got to be the water or the acid in higher concentration?
Oh, to clip off the silicon here, you want the water. In
Water
both
in higher
cases,
concentration?
yeah.
Okay.
And we use water in this instead of the fluoride, the ammonium fluoride, because we had to protonate the alcohol anyway. Because remember, when we do the Grignard reaction, we actually have the magnesium bromide salt that we have to clip off with acid anyway. And so we just added a little more of the dilute acid, heat it up for a little bit, and the silane goes away.
Okay.
And we can use that same workup if we did that T-butyl ether with the isobutylene. Okay, that is ethers. Okay, so that is module 11. So that is the last of that. With the remaining time, we have about 20 minutes left. I was going to start reviewing some of the other parts of chapters 8, 9, and 10. And then we can be prepared for our exam. Or would you like to talk about some of the other chapters? Remembering stereochemistry. I'll just open up the floor to any questions for this exam or the final. Let me go and I'll leave it recording so that.
Can we review like stuff for exam 3? Because that stuff is the most
Immediate. Right. So if we go to Canvas and we look at our files, there's a file called Exam 3 Hot Topics. The question is, so activity 4 is just over chapter 8. Yes, it's just over chapter 8 for this assignment, but if you continue to add in chapters 11 and one of the ones from chapters 5, 6, and 7, you'll start to build it up for yourself to help study for the final. Okay, so yeah, they're just two different formats. One is a bigger format, one's the little format. I used them both. But yeah, only for the assignment itself, only chapter 8. But if you find it helpful for you, you continue to do it. Yes, it was emailed out a week ago. Okay, you should have had it in a really mass email a week ago about assignment 4. If not, send me an email and I'll email it directly to you. So yeah, I sent it out to both classes at the same time. So, all right, let me go ahead and pull up my exam 3 review. So, and I'll share that. This is actually on Canvas as well. So what I wanted to do is, let's share my screen. I'll start doing that review. Chrome files, there we go. And actually, I gotta move this over here so I can see it. All right, screen pause. Let's go ahead and stop share and share again. There we go. Can you see the screen now?
Yes.
Okay. So what I consider these are hot topics. You need to look at them and go back to the homework and then explain, not that and try and get the right answer, but then explain to yourself why you got the right answer. If you can do that, then that really means you're really reinforcing the information as to, I can make the reaction work, but I also know why. Okay, that I think is the most helpful part of this, because as you follow on, you got to remember that we're going to use a lot of the same mechanisms that we've seen already, but they're just going to be applied to new substrates and new materials and new functional groups. So we want to make sure that we know why things happen. Okay, so of course in module 8 here, we took all these reactions with alkenes. Okay, and in module 8, we are looking at specifically things like whether or not there is regiospecificity whether or not there is stereospecificity and how the mechanisms are different, okay? When we have just HI adding across, we get syn and anti addition because of the generation of a carbocation. But we also get selectivity because the hydrogen adds first. If there's a possibility of making a more stable carbocation, it will. So those are the kind of explanations you need to be able to work through when you're looking at all the different reactions we have, you know. And then in hydroboration, you know, we actually change the way we do it. Put the boron on the less substituted atom. You know, when we do the mercurization, we do it a little bit differently and we get the alcohol in a different place. So we have our primary, secondary, and tertiary alcohols show up in different places based on how our mechanism works, okay? So knowing the rules on why Markovnikov's addition works is very important, okay? Do we get it at the more substituted side or the less substituted side? And because of the generation of a carbocation, that means we get attack from the top or the bottom, and therefore we have syn and anti addition, okay? In the halohydrin reaction, because we're forming that three-membered ring, we always get anti. But in halogenation too, we always get anti because we block the top, or we blocked at least one side of that, and we have to have the other bromine come in as the nucleophile from the other side, okay? So knowing the mechanism tells you whether it's syn or anti addition. It also, it works for both of them because of that bromonium or that three-membered ring, okay? In the hydroboration, it's backwards, both for electronic and steric features. This is the only way to generate a primary alcohol from a substituted alkene because the boron is going to add to the less substituted side the anti-Markovnikov's product. And then when you oxidize it off, you get that primary alcohol because oxidation does not involve a carbocation, and therefore you get your alcohol on that end. So I get a slide in that chapter about one substrate, three different alcohols. So make sure you review that as well. Okay. In the oxymercurization, demercurization, we actually get the alcohol on the more substituted carbon. Okay. And the type of selectivity you get with it by which way it adds gives you the stereoselectivity. So make sure you remember the stereoselectivity. And in the oxymercurization, demercurization, we actually have to reduce off the mercury. Okay. This slide, that's the one I wanted to make sure you understand why. In the tertiary alcohol, you're going through a carbocation intermediate. In the oxymercurization, you're getting mercury adding to the more substituted side. I'm sorry, the less substituted side, meaning your alcohol goes on the more substituted side, secondary alcohol. In the hydroboration oxidation, the boron adds to the least substituted, and when we oxidize it off, that's where the alcohol happens. Know why each of those shows up in a different place for the exact same substrate. Okay, let's see. Knowing the syn and anti, this is, I like to do this by remembering what the mechanisms were, because then it's not memorization, it's just, oh, because of the mechanism, it has to do this. I think that's one of the more important parts. We did oxidation states, increasing and decreasing oxidation states in the aldehydes and ketones, in the alcohols, and when we were doing the sodium borohydrides. We've done this in two different places. Okay. Looking at our different oxidizing agents and seeing if they are syn addition or anti addition. In the case of osmium tetroxide, we have syn addition. In the case of ozone, we actually clip the double bond and turn them into two ketones or two carbonyl compounds. So that's a really cool way to do it. Now, remember, if it's a reductive workup, you can stop at an aldehyde. If it's an oxidative workup, it does not start at the aldehyde and it goes to the alcohol. Questions on module 8. Okay, so that was all those cool reactions we had with alkenes. Module 9 is the alkynes. We learned how to synthesize them. We have to have at least 2 hydrogens and 2 halogens on adjacent carbons. Okay, they can be on the same carbon, then they can be on different carbons, and we have to use a strong base. Hydroxide's not a strong enough base. We have to use at least something like sodium amide to do it. Okay, and we need to remember that why the acetylene has that higher acidity than the other alkanes. It's that higher S-like content, gives it more stable negative charge, which makes it a stronger base. Which makes it a stronger acid. The more stable the negative charge is, the stronger an acid it is. And we can use that to our advantage to create a good nucleophile by deprotonating our alkyne. Okay. The addition reactions are very similar to the addition reactions we have with the alkenes, except we have to remember whether we're using one equivalent or two equivalents. If we're using one equivalent, we're going to get Markovnikov's addition there. And the second equivalent is also going to go Markovnikov's, meaning you're going to have a second equivalent that's going to put both halogens on the same more substituted carbon. Okay, so we can stop it with one equivalent or add two equivalents. With halogenation, we can stop with one equivalent, and it's going to give predominantly trans or anti-addition. Okay, it can rearrange a little bit, but it's going to give predominantly anti-addition. Okay. With two equivalents, you're just going to end up with 4 halogens on there. Okay. With reductions, you cannot stop at the alkene without having a less reactive catalyst. If you're using hydrogen with any of the regular metal catalysts, you will always go down to the alkene. The alkane, because that is the same catalyst we use to oxidize alkenes to alkanes. So we have to poison our catalyst. We have to use that barium sulfate and that quinoline. When it does that, we get syn addition. Because it's still a surface reaction, we get syn addition. But if we want anti-addition, we have to do a different reduction, the dissolving metal reduction. And the dissolving metal reduction works to give us our alkene in the anti-addition because we go through that carbanion. Remember, we're doing a single electron transfer, making a carbanion, which then abstracts a hydrogen, which then makes a single electron and gives us our intermediate. That second carbanion is going to be in that trans configuration. Therefore, we get trans addition. So for a cis addition, we need to use our Lindlar's catalyst. For a trans alkene, we need to use the dissolving metal reduction. Okay. So the reactions are alike but different than alkenes. Are hydrations, oxyborations, the potassium permanganate, and the potassium permanganate under alkaline conditions or basic conditions. Okay. Questions on chapter 8? Okay. Let's see, we still have time. Okay. 7 minutes. Module 9. The most important thing about proton NMR are these 4 things. Number of signals, that's how many different types of hydrogens you have. The intensity, that tells you how many protons are on each of those different types. Position, the further away from 0, the more electronegative, the more shielded it is, and the longer it takes to relax. And spin-spin coupling, the number of protons within 3 bonds of that peak plus itself equals your splitting. Okay, and those are all, know where they all are on the spectrum. And these common splitting patterns, or you can just do the counting thing, that works too. For carbon, we only have 2 things to worry about: the number of signals and those chemical shifts. And the shifts are in the same order as proton NMR. Okay, so if you get the order for the different substrates right for one, you'll get it right for the other. For mass spectrometry, all we care about is the molecular ion peak, which is the highest peak, the base peak, which is the tallest peak. The relative abundance of the different fragments tell us that whether or not we have like a methyl ketone or some other fragment that tells us we have like, a a mass of 15, that's a methyl group. A mass of 14, that's a methyl group. A mass of 15, that's a methyl group. You can see fragmentation. All right, questions on module 9?
I found the MS stuff pretty confusing. So you're just looking at what, radical stability for the fragments or what?
It's technically the bond association energy to form radicals. So the ones that we, in the radicals, when we think about the bonds that are going to break first under those bond association energies, it's the same thing. Those are going to be the ones we're going to form in fragmentation as well.
Okay, and then you just, for the peaks, it's the ion peak minus whatever the fragments mass would be, and that's what the peak will look like?
Yeah, that's what was broken off. So you take the one peak to the next peak, the difference here, that tells you what peaks broke off.
Okay.
And so like carbon is 12 and 2 hydrogens would make it 14. So a loss of 14 is a carbon with 2 hydrogens on it.
Okay.
15 is a loss of a carbon with 3 hydrogens on it.
Okay.
A loss of 17 is an OH. So you just look at what's leaving and equate that to some kind of atom and or group of atoms.
Okay.
Okay.
Thank you.
Okay. So that led us into radicals. And the most important thing about radicals is we have an unhybridized p orbital with a single electron in it. And we have 3 steps. Okay, sorry. The trends for bond association energy are very similar to the trends we saw in acid strength, okay? Electronegativity, size, hybridization, hyperconjugation, okay? Radical reactions always involve 3 steps. Initiation, typically breaking of a very weak bond using light or heat, like a halogen-halogen bond or an oxygen-oxygen bond. Every time a radical reacts with a neutral substrate, it generates another radical. That's our propagation step. That'll keep going and going and going until 2 radicals form a sigma bond and terminate the reaction. That happens in every single one. Now, we can use that to our advantage to actually, I was going to say using it as anti-Markovnikovs, but okay. But we also have the difference in the more reactive it is, the less selective it is. The less reactive it is, the more selective it is. So fluorine is very, very reactive because that's a very high bond energy and those radicals really don't like it. They're in a high energy state. They want to react as fast as possible. So fluorine is very non-selective. Chlorine's about in the middle and bromine has high selectivity because it has a more stable radical. And iodine doesn't react at all because that is a very stable radical and there's no reason for it to react. Okay, so it's all about radical stability. The easier that bond is to break, the more stable that radical is, the more selective it will be. Okay, and with this selectivity, it comes with, if you're non-selective, it's all about statistical value, the number of hydrogens possible. In the case of selectivity, it's all about the more stable radical you can form. And stability on radicals is the same as carbocations. Tertiaries are more stable than secondaries, are more stable than primaries. Okay, and therefore high reactivity, low selectivity, low reactivity, high selectivity. Okay, and then we can even make it more selective by using NBS to generate small amounts of the bromine radical to get to eliminate side products by reacting with bromine itself. Okay. And then these are the initiation, propagation, and termination steps right there. And this is what I was trying to say. In the case of halogenation, it goes anti-Markovnikovs because it wants to form the more stable radical. I'm sorry, it goes anti-Markovnikovs because in regular addition of HBr across a double bond, the hydrogen is added first and the bromine is going to be on the more stable carbocation. In radicals, the bromine reacts first, and therefore the radical is going to be on the more stable thing. So the hydrogen is going to be on the more stable. So the radical mechanism gives us an anti-Markovnikov addition, but it gives it an anti-Markovnikov addition for the same reason that we get Markovnikov addition in HBr. Okay. And we just did module 11. So we're right here at 9:20. Okay. All right, I'm going to go ahead and stop recording. And if you want to hang back and ask questions, please do.